in the Philippine province of Albay, where the Mayon Volcano continues to show signs of an impending eruption. Authorities say the alert level for the volcano might be raised again soon after this was placed at level 3.
Dr. Ana Delgado devoted 15 years to analyzing Philippine volcanoes as if each one were a separate geological entity. That assumption collapsed when she compared seismic readings from Mayon's January dome failure with archived monitoring data from Mayon Volcano, Taal Volcano, Mount Pinatubo, and Mount Bulusan. The waveforms were indistinguishable. The timing aligned with uncanny precision. Pressure signatures mirrored one another across hundreds of kilometers. What she uncovered upended conventional volcanic science. The Philippines was not home to dozens of independent systems. It was perched atop a single immense volcanic superstructure that was only now beginning to expose itself. Delgado's breakthrough study indicates that major Philippine earthquakes over the past 6 months, including the magnitude 6.9 Cebu event and the magnitude 7.4 Davao quake, systematically cracked the geological partitions that once kept magma systems isolated. Mayon's dome collapse was not a lone structural failure. It acted as a catalyst, activating an interconnected web of magma chambers linked through freshly fractured fault corridors. Subsurface pressure instruments now reveal synchronized magma migration across multiple provinces at the same time. The consequences are almost unimaginable. Delgado's computational models suggest that when any major volcanic center in the Philippines hits an explosive threshold, the resulting pressure discharge could ripple through the entire system within hours. Alert levels that historically rose over months might spike in minutes. Evacuation strategies built around single volcano scenarios become obsolete when faced with simultaneous multi-volcano activation. Her restricted reports pose questions that could transform global hazard planning. If the Philippine volcanic arc represents the first confirmed case of a connected supervolcanic network, how many other island nations are unknowingly positioned above similar geological time bombs? And if magma reservoirs can interlink across vast distances, how do we stop the next dome collapse from igniting the largest volcanic disaster humanity has ever witnessed? For 5 centuries, Mayon was viewed as a model of isolated eruptions. Since 1616, its 52 documented explosions followed a recognizable sequence: gradual dome growth, occasional flank collapse, localized devastation. Alert level 1 would rise to level 3 over weeks or months, giving communities time to flee. Then came January 2026. In only 6 days, Mayon surged from alert level 1 to 3, a breathtaking acceleration without precedent. Yet the speed of escalation was not what stunned scientists most. As Mayon's instruments registered tremors, Delgado observed something that defied explanation. Taal, 500 kilometers away, was recording identical seismic rhythms. Bulusan, 200 kilometers north, displayed the same harmonic tremors. Even Pinatubo, dormant for 3 decades, echoed the pattern. In a moment of chilling clarity, Delgado understood. These were not isolated volcanoes. They were interconnected nodes within a subterranean lattice of magma and fractured crust. When one pulsed, the others responded. The pieces fit together across the archipelago. The powerful 2025 earthquakes, magnitude 6.9 in Cebu and 7.4 near Davao, had effectively dismantled the geological barriers separating these systems. Pressure sensors now show magma coursing through newly opened conduits, linking chambers across hundreds of kilometers. When Delgado released her findings, they reverberated through the geological community. Volcanoes long studied in isolation suddenly had to be reassessed as components of a unified threat. A dome collapse at one could spark a catastrophic chain reaction at others. Her models depict a sobering scenario. Once pressure at a single volcano crosses a critical threshold, the cascade through the network could occur in mere hours. Processes that once unfolded over months might compress into moments. Evacuation frameworks designed for singular eruptions would fail against a coordinated volcanic crisis. These are not speculative musings. They are urgent alerts now reaching emergency planners throughout the Philippines. If Delgado's theory holds, the next major eruption will not erupt from a solitary peak. It will originate from an archipelago-wide supervolcanic awakening beneath more than 100 million people. To grasp the magnitude of the danger, we must look back 500,000 years. That is roughly how long Mayon has been active, fed by magma rising where the Philippine sea plate dives beneath the Eurasian crust. Over millennia, its eruptions sculpted one of the world's most symmetrical stratovolcanoes. But the elegance conceals tragedy. Mayon's recorded eruptions have killed over 1,500 people. In 1814, the eruption buried the town of Cagsawa, leaving only its church tower above hardened ash. In 1993, pyroclastic flows destroyed hundreds of homes and claimed 79 lives. Historically, these disasters followed gradual escalation, lava extrusion, flank collapse, localized destruction. Now, the foundational assumption of isolation has been shattered. Beneath the archipelago lies a violent tectonic choreography. The Philippine fault system stretches roughly 1,200 kilometers from Mindanao to Luzon like a fractured pane of glass. Each seismic jolt, including the 2025 magnitude 6.9 and 7.4 earthquakes, acts like a key, unlocking sealed magma reservoirs. Faults that once confined pressure now open channels, connecting distant chambers. Scientists long recognized that the Philippines rests atop converging tectonic plates and hosts around 50 active volcanoes. Yet they believed each volcano operated independently. Delgado's research overturns that belief. Her data indicates that when tectonic stress activates the right fault pathways, any volcano can function as a pressure valve for the entire system. A surge beneath Mayon could propagate toward Pinatubo almost instantly. A collapse at Taal might transmit destabilizing shockwaves across the network. Instead of confronting 50 separate volcanoes, the Philippines may be facing a unified volcanic engine with supervolcanic potential. Right now, approximately 200,000 residents are evacuating Mayon slopes. But if Delgado's projections are accurate, this may only be the beginning. Imagine Taal, just 60 kilometers from Manila, escalating in lockstep with Mayon. More than 700,000 people could fall within zones of ashfall and lahars. If Pinatubo and Bulusan simultaneously approach critical states, evacuations could sweep across Luzon. In a worst-case cascade, over 15 million people across 6 provinces might require relocation, an exodus unprecedented in Philippine history. The disruption would extend far beyond evacuation zones. Even minor eruptions impose flight restrictions within 6 kilometers. Now envision multiple volcanoes erupting simultaneously, ash plumes merging into a vast atmospheric shroud, grounding flights from Mindanao to Manila. Tens of millions of passengers could be stranded as ash clouds spread across Southeast Asia, crippling vital air corridors. Shipping routes through the Strait of Malacca and the South China Sea could be paralyzed. Infrastructure failure would follow swiftly. Nearly 40% of Philippine electricity comes from geothermal plants situated near volcanoes. A coordinated eruption sequence could disable those facilities, plunging much of the country into darkness. Communications would falter as ash damages towers and undersea cables. Highways, railways, and ports would clog with debris. Water reservoirs contaminated by ash could deprive over 25 million people of safe drinking water, triggering cascading sanitation crises. Globally, the economic consequences would reverberate. The Philippines is a major electronics manufacturer and outsourcing hub. A prolonged disaster would disrupt supply chains and financial systems. More than 10 million overseas Filipino workers could struggle to send remittances home. Emergency systems would strain past their limits. Military resources, already taxed by typhoons and security operations, could be overwhelmed. The crisis could escalate into a regional humanitarian emergency, with displaced populations seeking refuge across Southeast Asia. Meanwhile, a new era of volcanic surveillance is unfolding. At the Philippine Institute of Volcanology and Seismology, monitoring centers now operate continuously, integrating seismic, GPS, and gas emission data from across the archipelago. Scientists are racing to chart the hidden magma corridors linking Luzon, Visayas, and Mindanao. International teams from the United States, Japan, and Italy are contributing advanced monitoring technologies and crisis response expertise. What is happening in the Philippines may redefine how the world understands volcanic risk. Beyond the archipelago, researchers are re-evaluating volcanic regions in Indonesia, Alaska, and Iceland. Patterns once dismissed as coincidence, synchronized tremors, mirrored eruption timing, are being reconsidered under a new lens. If Delgado's hypothesis proves correct, traditional monitoring tools may be insufficient. Seismometers designed to track isolated quakes and gas sensors focused on localized plumes may not detect the complex crosstalk of an interconnected system. The reassuring buffer of weeks between tremors and eruption may be an illusion. In an interconnected volcanic world, a single dome collapse could ignite a cascade within hours. We are not prepared for that reality. But thanks to researchers like Dr. Ana Delgado, we are beginning to perceive its outline, a planet where the ground beneath us is more fragile and interconnected than imagined. The next Mayon, the next Pinatubo, perhaps even the next Krakatoa, may not erupt alone. They could represent the opening act of a synchronized volcanic awakening. The question is whether we will recognize the warning before the chain reaction begins.